Hey guys, we are going to talk about a couple of methods of property approximation in this video. Shouldn't take too long for this one. And what we're going to start out with is we are going to find approximations for liquids using the saturated liquid data. And remember that saturated liquid data, that's that liquid vapor mixture table that we've been using. That's what we'll be using for our approximations. What we're going to be looking for will be approximations for specific volume, specific internal energy, and specific enthalpy. Now, if we go to our compressed liquid table, which is table A5, we just look at water. If we go here and we look at U and V, so here's specific volume, here's U. If we look at the same temperature and we look at how these values change as we increase the pressure, you'll notice there's not a lot of difference. So let's look at this top one. So at 20 degrees, 25 bar, V in the table is 1.006. Over here, it's 0.9995. Those numbers are pretty close. Same thing with U. We got 83.8. Over here, we got 83.65. And as you work your way down the table, even though we are increasing pressure quite a bit, these values aren't really changing a whole lot. They're changing a little, but not a lot. Okay, so because of that, we can use the liquid vapor mixture table as an approximation for compressed liquid. Okay, so that's what we're going to do. So since we can do that, we can say that specific volume, which normally is a function of temperature and pressure, we can say that that is approximately equal to VF. That's that saturated vapor point for our specific volume, and you'll just find it at your given temperature. So basically we're saying pressure is not really going to matter at this point. We care about the temperature, so at our given temperature we're going to find VF. That's going to be good enough for us for compressed liquid. Same thing with internal energy. So little u, specific internal energy. We're going to say that value, which is typically a function of temperature and pressure, we're going to say that's approximately equal to UF at the given temperature. Now, if we get to the F point, if you think back to the vapor dome here, this point right here is F. So F is basically where we switch from compressed liquid to the start of the liquid vapor mixture. So essentially we're kind of ignoring all of this down here, and we're saying all of the values of V and U for this section are going to approximately be equal to this location right here. That's basically what we're doing. So it's just an approximation that you can use. So let's write down that we can use the liquid vapor mixture table as an approximation for compressed liquid. And if you notice when you're working through some of the problems, you might have a compressed liquid, you've done the work, you've figured out and decided, yeah, I have compressed liquid, I need to go find this information in the table. You go look in the table and that information isn't given to you. So if it's not given to you in the table, you can always use this approximation. Right, so it gives you something to fall back on. Now we have the same thing with enthalpy. So we can say our enthalpy, which normally is a function of temperature and pressure, we can say that that is approximately equal to UF at the given temperature plus the pressure times VF at the temperature. All right. And another equation we can use, we could rewrite that and say it's approximately equal to HF of the temperature because notice this is H, because U plus pressure times specific volume, that is specific enthalpy. So we're just replacing this with H, and then let's do plus VF of T times your pressure minus the saturation pressure at the temperature. I ran out of room here. Okay, so that's another equation you can use. And if this is small, if your VF number is pretty small, this term is going to be small. So if that's the case, then your specific enthalpy is going to approximately be equal to HF at the given temperature. All right, so this just gives you a couple of ways to approximate enthalpy and specific volume and specific internal energy. And this is going to work for any substance. So it's not necessarily just for liquid water or compressed water. Okay, it'll work for any of the substances we're going to be dealing with. Okay, so that's one of the approximation methods. The next one is going to be the incompressible substance model. Now, when we say incompressible substance, let's talk about what that is. An incompressible substance is going to be one in which rho, which is density, or your specific volume, doesn't change. Okay, so density is going to be constant. Same thing with specific volume. Our internal energy is only going to vary with temperature. Okay, so we can write this and we can say V is constant and U, oops, forgot something here. U is just a function of temperature. And when I write things like this, we're basically saying you just have one temperature, and that temperature is all you basically need to find that U value. Pressure is not going to matter in this case. Now, if we have an incompressible substance, we're going to say the specific heat, constant pressure Cp, is equal to the specific heat of constant volume. All right, so if our density doesn't change and U only varies with temperature, we can make this claim right here. And since these are equal, we're just going to use the variable C instead. So there's no need to have Cp and Cv when they're the same value. We'll just call it C. Now, we already said U is a function of temperature. So since U is going to be, not U, keep writing the wrong thing, guys. Let's put C. Since C is du dt, then we can go ahead and write our specific enthalpy, function of temperature and pressure. That's going to equal our specific internal energy at our temperature plus P times V. And these will be constant, or V is going to be constant. So now we have that relationship. So let's go ahead and expand on that. With this, if we know C is equal to du dt, if you think about it, you can rewrite it like that. Integrate both sides. And then let's put the U terms on the left. We'll have U2 minus U1 equals C times the change in the temperatures. And now if we take this enthalpy here and we look at the change in enthalpy between two states, we can write that H2 minus H1 equals C times T2 minus T1, which we got from right here, plus V, because V is constant, times P2 minus P1. And usually this is going to be small. So a lot of the times this is going to equal 0. So if you ever see h2 minus h1 equals c times t2 minus t1, that's because this term here is going to be a lot smaller than over here, so you can neglect that one. Okay, so here are a couple of other equations for you. And those just give you some approximation equations. And as we go through our examples, the rest of the class will occasionally come back to these. So just remember, this is where we're getting them from. Okay? We're just making assumptions here. Approximations. That's the end of this video. We will pick it up next time with the compressibility chart. See you then.